Good afternoon, everyone. My name is Sam Schwartz, and I will be your moderator today. And welcome for all the AABC members and all non-members coming for another Tab Talk webinar. I'm going to go over a few housekeeping notes before we get started. We do encourage you to submit questions at any time using the Q&A button, but we will be holding the Q&A session until the end of the presentation, but please do not hesitate to submit them as we move forward with the presentation. The chat function is where you can make general comments and chat with attendees. And if you happen to be experiencing any issues or technical problems during the webinar, please use that chat function to inform the panelists, and we will assist you. And finally, this course has been approved for 1 hour of continuing education credit. After the webinar, you will receive an automated email with your proof of attendance. And a little bit about our speaker today, Jeff Keene. He's professionally certified TBE, CXA, and EMP. In 1994, Jeff embarked on his journey with Delta T. Throughout his career, he demonstrated exceptional dedication and skill, steadily progressing in his role within the organization. And in recognition of his outstanding contributions, Jeff has achieved the esteemed position of principal at Delta T in 2013. So without taking any more precious time today, I'm going to hand it off to Jeff, who's going to talk about humid buildings. Jeff, take it away.
Thank you, Sam. As Sam mentioned, my name is Jeff Keene. I've been with Delta T for quite a while, and we wanted to talk a little bit today about humid buildings because nobody likes humid buildings. So
Hey, Jeff, I think you muted yourself.
I did. I apologize. Sorry about muting myself, but as I was trying to say, we do have some poll questions that we're going to pop up throughout the Tab Talk. I'd like to start with the first one now, just so we can get an idea of who we have in the audience, so I can modify and tailor this more to the clientele that we have. So the first question is, what's your primary role, whether you're a TAB professional, architect, commissioning agent, or facilities or building engineer? Again, this just sort of helps me understand who we have in the audience, and it'll help me later in the question and answer portion so I can address questions and answers more appropriately. Okay, great. It's a pretty even split. That's good to see. So our abstract is Delta T. The most common problem that we see that we get called in for are humid buildings. And with that being said, we're going to look at 3 different projects today. They all 3 had different components to their systems, and they all 3 resulted in different resolutions to achieve a comfortable building at the end. And our learning objectives for today, we want you to be able to effectively identify the source of your humidity. We're hoping that you'll understand the significance of good and bad sequences when it comes to humidity control in your building. We want you to be able to educate your end user at some of the primary do's and don'ts for humidity control. And we want you to gain some insights on critical aspects of a project that you should never overlook to help prevent any type of humidity problems that may come up. The first project that we're going to look at is junior high school. That was a remodel project. We did not do the original tab. The tab was done by an NEBB firm. They continued to have problems, so they brought us in This project is located in South Texas, about 40 miles from the border of Mexico. It's a really hot and humid climate down there. The classrooms were all chilled water fan coil units with dedicated chill water makeup air units. The admin areas and the elective areas were central station air handlers with VAVs serving those areas. The larger gyms, kitchens, band hall, auditorium, they were all constant volume chill water air handling units. Of course, since it was a central, since it had chill water, we had a central plant. The building temperatures averaged about 68 degrees when we first started looking at this project. Pretty much everywhere was between 67 and 69 degrees. The humidity levels averaged around 65%. One of the wings was well above 70%. We typically don't ever want to see humidities above 60% on any project that we deal with. The main complaint was in the classroom areas of this school. That's where they originally asked us to look at the problems at. And we were provided all the plans, the specifications, submittal, and they provided us the test and balance report for this project. So that's what we started with. So our initial steps were to try to actually identify what the problems were in this school. They told us it was a classroom wing. We typically get the information when we're brought onto a project like this from either the superintendent or a facility manager or something like that. They aren't always apprised of how deep problems may go. They also may over exaggerate problems in specific areas, just depending on the complaints that they have. So we want to make sure we identify all the problems. We do this by talking to the staff. We typically would not want to talk to occupants during our procedures, but in this particular case, we do want to talk to the staff. We want to look at the work orders that have been produced on the project, and we want to review all the trends if they have any trends. If they don't have trends, of course, we'll set trends up first thing. In this case, it was determined that the classroom areas were the primary areas of concern. So our next step was to go to the plant level. We took measurements at the plant, checked the chillers out, checked the pumps out, made sure everything was operating correctly, or at least determined a baseline of where everything was operating. We did the same thing with all the makeup air handling units. We traversed the units to get total flow. We measured GPMs, temperatures to determine a baseline for the makeup air units. We did a large sampling of the fan coil units, doing the same things, taking all the airflow measurements, temperatures, GPM readings. And we went through the sequence of operation to determine exactly what the sequence was. And when we go through the sequence of operation, we're actually going through what's on the site, where even though we were given control drawings, we wanted to see how it was actually operating. One of the things that we did not do, that we typically will never do, is we didn't bother looking at the tab report, even though it was provided. We typically won't look at the tab report. If we've got a problem in a building, we find that it doesn't really do us any good. The only caveat to that is we will see who did the tab. If it's a AABC company or it's a company we're familiar with, we typically will, out of courtesy, just contact them to let them know that we are going to be looking at a project that they completed. So what we found on this building was the central plant seemed to be working pretty good. We had correct flows at the chillers. Chillers were performing. The one thing that we did notice that there was only a 5-degree delta at the chiller. We really were expecting to see about a 12-degree if everything was working correctly. When we have a low delta like that, it typically indicates to us that we have an unbalanced water system. When we looked at the makeup air units, total CFM of the makeup air units were all correct. They looked good, but when we measured the GPMs, they did not match what the submitted GPM rating for the makeup air units. On the fan coil units, the total CFM seemed to be correct, but the outside air was not correct going to each one of the fan coil units. So it appeared that the makeup air units were set for total, but they weren't proportioned to the fan coil units. And again, the GPMs were not within design parameters. The sequence called for the makeup air handling units to modulate the chill water valve to maintain 55-degree discharge air. That's what they were doing, but since the water was not balanced, we noticed that we had one unit that was able to deliver the 55-degree air with the chill water valve just cracked open at 5%. We had another one that was delivering 63-degree air with chill water valve 100%. Again, indicating what we already knew, that the water had not been balanced or needed to be balanced. The fan coil units, the way the sequence called and the way the sequence was working was that for the chill water valves to modulate to maintain space temperatures. We had no problem maintaining space temperature. As we indicated earlier, the average temperature in the building was about 68 degrees. And the majority of the units were maintaining the temperature by modulating the valve and discharging temperatures between 56 and 64 degrees. So typically you want a design condition of about 70 degrees, 50% relative humidity, give or take a couple of degrees. That's typically where we want everything to be. We were way off from this. Our room conditions in this particular space were 68 degrees and 65% relative humidity. Whenever we're looking at a humidity issue in a school, what we're looking at is the grains of moisture in the project. So if we go back to the design conditions, typical good room conditions, we're running about 58 grains of moisture. That's where we'd like to be. In this particular case, we are running more like 68 grains of moisture. So the key is to determine what needs to be done to get that moisture out. You'll also look that, considering that the outside air is conditioned in this particular case, you're going to have a mix between the conditioned outside air and the room temperature that you've got to remove the moisture from. The room conditions dictated that we needed at least 56-degree discharge air to reach dew point. And most of the units were not delivering that. This is just a blow up because it's hard to see that psychrometric chart on the first page. But again, you can see that we're running about 68 degrees, 65% relative humidity, which indicates that we've got 68 grains of moisture with a 56-degree wet ball or dew point, This is a sample of one of the trends that we took. This particular trend, we were taking readings about every 8 minutes. We will adjust that time depending on what the trends look like. 8 to 10 minutes is usually a good starting point. You can see the lowest temperature that we typically would reach was about 56. The highest temperature was about 64, averaging about 60-degree discharge air on these fan coil units. And we know from the previous slide that we need at least 56 degrees before we can remove any moisture from that building. So the conclusions and the resolutions that we had for this was, the primary thing is the water needed to be proportioned. We needed to make sure that we could get design water flow at all the equipment, so the equipment can perform the way the manufacturer intends for it to perform. So the water got proportioned. We needed to proportion the outside air. We needed to make sure that each unit was getting the right amount of outside air. Outside air is critical because we need to make sure that the building stays positive and that we're meeting the code requirements for ventilation. We typically request that the room temperatures get adjusted between 70 and 74. One of the common things that we see in buildings that have humidity problems, the first thing that gets done is the outside air usually gets shut, which results in a negative building, and which the outside air is going to come in the building one way or the other, whether it's going through a piece of conditioned equipment or whether it's coming through the doors and any other place that air can get if the building's negative. The other thing that we see is people will drop this temperature set points, hoping that, well, a colder building units will run longer, therefore dehumidify better. That's never the case. The way, we always tell the owners the way relative humidity works is it's relative. That 65% relative humidity building at 68 degrees is going to drop down to 60 or so if you raise the temperature, up to 70. That doesn't mean that it's comfortable, but again, relative humidity is relative, and that's why we look at grains of moisture when we're dealing with humidity control. One of the main things that we needed to do was we needed to change the sequence of operation on the fan coil units to make sure that the fan coil units could achieve dew point, because currently the way they were modulating to maintain space temperature, they were never reaching dew point. So the way this is done is since we have makeup air unit that's conditioned, the fan coil units ran continuously and the chill water valves cycled open or closed for demand for cooling. So during occupied time, the fan coil unit just ran, getting its conditioned outside air. If there was a call for cooling, the chill water valve would open 100%. We'd reach dew point without a problem. Once demand was met, chill water valve closed. That resolved all the problems at that particular school in South Texas. Once those conditions were met, we no longer had any problems. Again, the key was to make sure that we were reaching dew point when the units were running. The next project is an elementary school. This is additions and renovation. This is a project that we did do the original test and balance on. This project is located near Houston, Texas. This project was all DX. The admin area had DX rooftop with hot gas reheat. The library and cafeteria areas were all DX with DX dedicated outside air units. These were both new areas. The admin area and the library area were both new areas to the project. The renovation were all the classrooms, which were DX split system fan coil units with DX outside air units serving the outside air for all the fan coil units. The building EMS on this project was very limited. It was, for all intents and purposes, a glorified time clock. It just enabled and disabled based on occupancy. The controls were all internal to the equipment. We did have some ability to change set points for room set points. We added some ability to get some data back from equipment later on. Again, our initial steps are always going to be similar. We needed to identify what the actual problems were by looking at the work orders, talking to the staff, reviewing the trends. And in this particular case, the primary concern was the media center of the library. Although we did have sporadic complaints throughout the buildings, the main issue was the library in this particular case. Again, on all of our initial steps, you'll see that we're not relying on what somebody's telling us the issue is. We're trying to determine by a systematic means what the actual problem is on the project. So we measured all the outside air units. Again, even though we did the test and balance, we reread every outside air unit on the project to make sure the CFMs were correct and that the units were performing the way the manufacturer indicated it should. We measured all the DX units that served the media center and areas of concern. And then we went back through and we re-verified all the sequence of operations on the project. On this one, we also took some thermal scans of the building. We utilize thermal imaging camera quite a bit for troubleshooting procedures. If you don't use them in your trade, whether you're commissioning or test and balance, we highly recommend it. It's not hard to get a thermography certificate, and it's very beneficial when trying to troubleshoot things. On projects that we have an issue that we did the test and balance, we do verify. We do go back to the test and balance report. We never send the same crew. We send another crew out and we verify the readings that we're taking during the troubleshooting procedure to the readings that were on the test and balance report. We do this for quality control. We do it to see what, if anything, has changed between our initial readings and our final readings. But we do, when we do the test and balance and we have a problem, we do go back and verify against the tab report, which is something that we do not do if we did not do the test and balance. What we found on this particular project were, fortunately, CFMs on the outside air units were right where we had them on the test and balance report. So that was a positive. But the trends indicated that the units were not always operating properly. The discharge air was not always where it needed to be. On the DX units, fortunately, again, the CFMs were correct. The outside air was correct. So as far as the proportion was concerned, everything was within design parameters. But we did discover multiple mechanical issues. We found some dampers that were not closing properly. We found a myriad of sensors that were unplugged on units, whether it be sensors or modules. We had a lot of compressor failures on equipment, relief dampers that were broken, thus allowing outside air to be able to be drawn in through the relief. So we did find a lot of mechanical issues. That was determined some of these mechanical issues were failures, and it was also determined that some of these mechanical issues were because the owner just decided, well, let's just disconnect this stuff and see if we can solve the problem ourselves. The building, fortunately, was positive, so we didn't have a problem with the building being positive. And during our thermal scans, we did indicate that there's possible envelope issues with the building. Nothing major, but we did identify some areas of concern. Of course, we always want our buildings positive, but moisture migrates. You don't have to have a negative building to have a humid building if you've got a really bad envelope, because moisture is going to migrate, and if you don't have a good building envelope, you will still have problems even if the building's positive. This is just an example of the trend data that we were looking at on one of the makeup air units, one of the dedicated outside air units. You can see it was all over the place. It rarely ran in that 55-degree temperature range. Again, this one was supposed to deliver 55-degree air to the rooms, and it never did. I have another trend here that shows this is after we had all the corrections done. We were able to achieve that 55 or close to that 55. These are some examples of the thermal scans. You can see the discoloration or the inconsistent coloration in the upper center part of the left-hand picture. This is indicating that we've got some thermal change behind that wall. We've got a scupper that you can see on the side, similar change in color. Again, these aren't massive issues, but they were things that we needed to point out during our investigation. On this particular project, our conclusion and resolutions, well, first thing we had to do is repair all the mechanical issues. If we have compressors that are failing on these makeup air units and we can't condition the outside air, that's going to kill us. And our region, at least, the primary cause of humid buildings is the unconditioned outside air. We've got to bring in a pretty good amount of outside air to meet code to keep buildings positive. And if we're not conditioning that air, it's always going to be a problem for us. We also modified the EMS system on this particular project to enable an alarm to come back to the owner if the discharge air temperature was not being met on the units, on the outside air units. So anytime the outside air was above set point for a certain amount of time, it would send an alarm notifying them that they needed to look at it. We also modified it to where if it couldn't meet discharge air for an extended period of time, it would just shut down the unit, because with that unit delivering so much outside air that was unconditioned, that was really humid, it would really raise the humidity levels quickly in that building, to the point to where you'd have books curling and potential growth inside the building, which of course we don't want. So we had it modified to shut the units down if the units couldn't deliver the right amount of outside air or temperature of outside air. And then we talked to the staff. We spent a pretty good amount of time making sure the staff understood closing the outside air dampers isn't a good idea. Dropping the temperature isn't a good idea. And more importantly, we spent time making sure that they understood how those outside air handling units were to operate and what they needed to look for. It's not uncommon for us to see building operators disconnect things like we saw on this particular project. But most of the time they do it because they don't know any better. So we always like to spend time with the staff if possible, making sure that they understand the equipment that they've got and what they need to do to troubleshoot the equipment that they do have. Once all the equipment was running correctly and we were delivering the right temperature outside air and all the mechanical issues were fixed, we were able to maintain temperature and humidity in the buildings without any problems. And it was determined that there were no modifications that needed to be made to the building envelope. Even though it may have been slightly compromised in some areas, it wasn't compromised bad enough to result in some corrective features, which would have been pretty destructive features to correct the building envelope. It's never easy to correct building envelope issues. So that was the second project. The next project is another project that we did not originally do the test and balance on. This was a brand new high school. This high school was located in Oklahoma. The first day that I showed up at this high school, there were news crews out front, which is never a good sign. So this particular school was all DX. It had DX central station air handlers with VAVs that served the classrooms. All other areas were either constant volume rooftop units or split system AC units. They did not have any dedicated outside air units on this particular project. All the outside air was being brought in through the hoods on the rooftop units, or it was ducted directly into the returns of the split system ACs. Again, the temperatures did range in this building between 68 and 72 degrees. Our humidity levels ranged between 60 and 75 when we first got there. And the main complaint in this area, or in this building, was the library, band hall, choir room, and cafeteria. So the main complaint was in the areas that had the large RTUs that were constant volume. Again, when we start, we always make sure we have plan specification submittal, and they provided us the tab report. Again, this tab report was done by a NEB company, which is no longer in business. And we didn't bother looking at the tab report. I will say on both the jobs that we did not do that was that were performed by NEB companies, there was no water data in the first report. So they obviously, I mean, we knew that from our testing, they didn't do the water, and there was no water data provided. So at least they didn't falsify the data. And on this particular school, there were no temperatures. They had air readings, but they didn't have any temperature readings on any of the equipment. So I did notice that we had some design and facility people in the audience. It's a good thing to look at your test and balance reports when you get them, to make sure that you've got that data, because if they don't have that data, it's not very helpful. So again, our initial steps are the same on every project. We looked at work orders, we talked to staff, we looked at trends, and like they told us, the primary area of concern were the large areas that had varying loads, like the libraries or the gym, where you could have 10 people or you could have 150 people. Went through the same procedure. We always take measurements on any problem project. So we measured all the rooftop units, total CFM, ran them through our paces, took temperatures, verified all the sequences of operation on all the equipment, ran them through their procedures. Once again, we did not look at the tab report. Again, like I said a minute ago, we did look at the tab reports after the fact just to see what data was in there, but we don't use existing tab reports when we're trying to identify what the problem is on a project. What we found at this particular project, the majority of the units that we measured had CFMs that were above the specified CFM, which is always a problem because we cannot do the latent capacity at a higher CFM. So almost all the units were more than 10% above specified capacity. Even those that were within specified capacity were at the higher end. They were 8 to 10% above specified CFM on the units. Most of the units, if not all the units, had the outside air dampers closed. Again, this was most likely done by the staff because they had a humid building. They need to resolve the humidity issues. So the first thing they do is shut down the outside air, which of course did not solve their humidity problem. That's one of the things that we try to stress to clients is I haven't seen a project yet where dropping the temperature down to 66 or 68 or shutting the outside air, that's never solved their problem. So we always recommend that they don't bother trying to do those two things because it's not going to fix the problems. So the building was negative since the outside air dampers were closed, which again, like I mentioned earlier, the outside air is typically our main cause for humidity concerns. And whether it's being brought in through doors or the equipment, the outside air is going to come into the building. One of the major things that we saw are the larger RTUs that had multiple compressors and 2 and 3 stage units. The majority of the time they were operating in first stage, which is common. Even now when we see digital scroll compressors and MSAV type RTUs, they typically are going to be operating on the lower end of the spectrum of capacity. The problem we have with these larger RTs on this particular project is they were all single speed fans. None of the fans had VFDs. None of the fans were ECM motors. There was no way to adjust the speed except through pulley adjustments, shiv changes or adjusting the shivs. So no matter what stage the unit was in, it was always delivering the maximum CFM that it was capable of delivering. So around here, at least, our design entering air temperature conditions are 80 and 67. So 67 degree wet bulb, 80 degree dry bulb. I've just represented this on a psychrometric chart so you can see, if we've got those design conditions, dew point needs to be at least 60 degrees. So we need at least 60 degrees leaving those units in order to remove the moisture. Again, I have a thermal scan of a diffuser, and believe me, I understand that that 65.8 degrees that's showing there doesn't necessarily represent the air temperature. That's the surface temperature of the grill. But we did take actual readings of the equipment, and this is with the piece of equipment operating under normal circumstances, which was in first stage. We were nowhere near what we needed to get to achieve that dew point temperature leaving the unit. So the conclusions that we came to and the resolutions that we had to identify and take care of on this particular project was we went through and adjusted all the units. We adjusted most of them on the low end of the spectrum. So If it didn't have multiple stages, we would typically adjust the unit down to about 350 CFM a ton to try to increase our latent capacity. Because again, the higher our CFM, the less our latent. So we wanted to get as much latent capacity as we could. So we went through and adjusted all of the rooftops to the lowest CFM that we could by manufacturer's recommendation. We adjusted all the outside air. So we had to go through and adjust the outside air on all the equipment to make sure that the building was getting the right amount of outside air to meet code and to keep the building positive. In doing so, we noticed that even though once we had the outside air set, we still weren't positive. And since we initially were just looking at the humidity issues in the building, we didn't initially take any readings on the exhaust system of the building. But once we had design outside air everywhere, we noticed the building was still positive. So that resulted in us going back and verifying the exhaust throughout the building and adjusting the exhaust accordingly to make sure that the building was positive under normal conditions. We have a really good relationship with this particular manufacturer. So we were able to get, even though this job was in Oklahoma, we had some Dallas reps for the unit manufacturer to come up and assist us with modifying the sequences. Some of the units we ended up derating. So we may not have needed the capacity that was there. So with the manufacturer's assistance, we changed the sequences to where on some of them, they, instead of starting the small compressor first, they started the larger compressor. It just depended on the unit, what we needed to do to make sure that unit was reaching dew point when it was running the longest we could get it to run. Because the key to removing the moisture is to reach that dew point and to keep it at dew point as long as possible. And then on some of the units, there was no other choice besides having the manufacturer install some VFDs and modify the unit to where the fan would adjust depending on the staging. That way, if we had a 10-ton unit with two 5-ton compressors, we weren't delivering 4,000 CFM when we only had one 5-ton compressor running. And in this case, again, with the manufacturer's blessing, we reduced all the CFMs throughout the project to about 350 CFM a ton. On equipment now that we see with the digital scroll compressors and ECM motors, we see a lot of systems that are designed at way less than that to increase latent capacity. So once that was done, we had no problems with that building. The building worked fine. Again, we worked with the owner. The manufacturer was able to offer them some services as well as far as monitoring the system, and it's helped us in a long-term commitment with that particular client. Several things that are really important to keep in mind when you're dealing with projects is, I mentioned this multiple times, but is the building positive? And quite frequently what we find is the building may not always be positive. The building, a prime example is the kitchen hood may run from 10 o'clock until 1 o'clock. And it's frequent that when the kitchen hood comes on, some of these schools do become negative. But we always look to see if the school is design positive, because we've even seen some projects that if you add up the outside air and you add up the exhaust exceeds the makeup air going to the building. So we'll look at the plans to make sure it's design positive, and then Of course, we need to verify by taking readings and checking the systems to make sure that the building is in a positive. You typically want a slightly positive building. Of course, you don't want the doors blowing open. You don't want to waste energy, but air's always going to travel to the path of least resistance, just like water. So if it's negative, air is going to come in, outside air is going to come into the building. Actually, at this point, I think this is a good point to actually bring up the second poll question that we have, Simran, if you don't mind. Because I'd mentioned our main issue that we see is humidity issues, but what are the most common issues that the people here attending this tab talk, what are the main issues that you guys see? Is it humidity? Is it building pressure? Is it temperature? Or do you have other? Because I know at the last convention that was here, we had somebody from Alaska that gave a talk, and of course he's experienced some problems that I would never think about, because the conditions in Alaska are vastly different than the conditions here in Texas. And I imagine if you're a technician or a company in Arizona or Nevada, you're probably not dealing with the humidity issues that we're dealing with, because I typically am localized to the problems that I have here that we deal with. So yeah, it's pretty even between temperature and humidity, and then we have a few in for building pressure, slightly less for building pressure. So that's interesting to see. Yeah, fortunately for us, temperature problems aren't one that we see a whole lot. And typically, if we have temperature problems, they're pretty easily resolved, because they relate back to equipment problems, from our experience, at least. So the other thing that's, again, I've brought up multiple times, I had a couple of slides that had the psychrometric chart. We use the psychrometric chart a lot when we're evaluating buildings. It really helps us to see if we're removing the moisture, or if we're not removing the moisture. But the next key is, are we reaching dew point? So is the discharge temperature of the unit going to dew point? We have a lot of projects where they want the discharge air temperature to reset for energy savings, and that's fine. We have no problem with that. But we always try to make sure that whatever that reset is, that we're never risking the chance that discharge air temperature is going to be above the dew point, to where we can't remove the moisture. Another key factor is it reaching dew point at all stages? That last job that we did in Oklahoma, the units were tested in full capacity. So that 10-ton unit that I referred to earlier, even though they didn't have temperatures, even if they'd had temperatures in there, that unit, was designed at about 4,000 CFM. It was probably doing 4,400 or so. Those temperatures may have been at dew point at maximum capacity. But if it was only running in first stage, if they had taken temperatures, they'd have noticed that there's no way that unit can maintain discharge air temperature below dew point when it's in first stage. We do this on all projects, whether it's a conventional DX unit like that. Most of the units that we see now, like I said, have ECM motors or digital scroll compressors. And anytime that we have multi-stage units or units that vary in volume, we verify that we're always able to dehumidify when that unit's running, because if it's not, if it's only doing sensible BTUs and it's not doing any latent, it's not helping us at all. Another key factor is the discharge temperature at dew point for long enough. So the very first job that I ever did by myself here, units we just changed code to where we had to increase the outside air. I was nervous because it was my first project. I had to make sure that everything was right, and I did. And we had all kinds of humidity problems in the project. What we noticed is that when the unit ran, it would reach dew point and, work fine. Problem is, it would only run for about 5 minutes at a time. It was short cycling. So as it short cycled, it was just pumping that humidity right back into the room. So the unit's got to run long enough in a cooling mode to be able to actually condense the water and have the water drain out of the condensate. And then, are there obvious building issues? Do they keep doors open? Are there operable windows? Is it an old building that could possibly have a bad building envelope? That school that was in the Houston area that we did, one of the things that came up when we were doing our investigation is during the morning hour when the buses were coming in, they literally would stand there with all the doors open in 2 different locations of the school for about an hour and a half, from about 7 until 8:30. As buses and occupants were coming in, they just had staff standing out there, and they kept the doors open, which again, moisture migrates. So even if that building's positive, you're going to add humidity to that building in the Houston area. So we see projects, older schools, older buildings that have operable windows, and they'll have the air conditioning on and the window open because they want the fresh air. So, it's always important to look at the building conditions itself as well. So with that concludes my presentation. I think Sam's going to go through some of these questions that we have, and I'll answer them the best that we can.
Thank you so much, Jeff. So we have about 6 minutes left, so let's jump into the questions. And if anyone else has any questions out there, feel free to submit them with the Q&A button. So Jeff, the first question is, how did you set up trends with the DX unit and limited EMS?
So on those, what we typically have to do, if they've got an EMS system at all, it's typically capable of doing the trends, whether they're set up or not. A lot of times you'll have to have them bring in more points to look at it. And that's what we had to do in that particular case. The one that had limited EMS, the outside air units, for example, they did have a backnet card on them, to where they could see anything and everything that outside air unit was doing, but that's not what was in the original scope. The original scope just told it to tell the unit to turn on and tell the unit to turn off. And like on the rooftop units, similar thing, they were telling it to look at the room temperature. So you could trend the room temperature right off the bat, but there wasn't much other data that you could bring in. We have experienced problems where there is no backnet card, or we've even had projects where there was no EMS system, and it does create some problems. We have a series of data loggers that we put in projects like that throughout the building, and we trend the data that way.
Perfect, thank you. We got another comment, really. I found that school district maintenance will manually adjust OSAD closed in an effort to improve temperature desert climate. And then they also added resulting pressurization problems, as well as IAQ and CO2 levels.
That's I agree with that 100%. I'd mentioned that that's the very first thing that we always see is the districts shut the outside air. They'll do it for a myriad of reasons. They either do it for temperature, they do it for humidity, they do it for energy management to try to reduce their energy bills. They do it for 1,000 reasons. And again, that's why I talked about working with the clients to try to educate them on the do's and don'ts of what you don't want to shut the outside air. If we're not maintaining temperature correctly, or if we're not maintaining humidity correctly, then there's other issues that we need to look at, because we do need to bring in that outside air. As Robert said, for code, we need it for indoor air quality. We need it to keep the building pressurized. So that's I agree with that, and that's why we try to educate our clients on one of the don'ts is not shut the outside air.
Thank you. We have another comment from a member that I personally very much agree with, surviving DC summers. They said that 74 and humid feels a lot hotter than 78 and dry. And that, or rather, you don't really sweat when it's humid, or rather, the sweat won't evaporate and cool you as well when the RH is high.
That is true. And again, I agree. As I'd mentioned, we ideally, you don't want your building at 68 degrees. Again, energy consumption wise, it's not good. We have teachers that get extremely cold when it's 68. We have others that, want at 65. But, I see a comment here that perceived temperature is a combination of temperature and humidity. And of course, that's correct. And yeah, if it's 65% relative humidity and 68 degrees, that perceived temperature is not going to be real terrible. If you move it up to 70, it's still not going to be comfortable in either case. When you have humidities that are in the 70 percentile range, I don't care what you do, it's not going to be comfortable, because you can get that perceived temperature down by really cranking the temperature down, but then you're just cold, even though the humidity level's high, and it poses other problems. So, sort of like with the outside air dampers, that perceived temperature is correct, but you need to look at the root cause to see why that perceived temperature is where it's at. Because if you can get it closer to that 72 and 50% range, somewhere in that ballpark where your grains of moisture down, around that 58 grains of moisture per pound of dry air, rather than 74 or 78, that perceived temperature is going to be a lot better off.
Thanks, Jeff. I did want to include this one last question, and then we can wrap things up. What is the top factor that causes high humidity in a building?
For us, it's outside air. It's unconditioned outside air. I mentioned that first project that I ever did. When I first started at Delta T, the rule of thumb is you had about 10% outside air on everything. And they were oversized in all the units. So in an elementary classroom, they'd have a 5-ton unit, and 10% outside air, and they didn't have problems. And then they switched to the new standards, and they went from 150 to 200 CFM outside air to 350 CFM of outside air, and they kept that 5-ton unit on there. You're bringing in a lot more outside air, and we weren't dehumidifying it. That's why I harp on a positive building. Out for us, at least, outside air, unconditioned outside air, or untreated outside air, is the biggest culprit for humidity problems for us that we see.
Perfect. Thank you so much. That is all the time we have for the Q&A today. If you did have a question that was unanswered, we will be sending the Q&A report to Jeff so he can follow up as he sees fit. Jeff, thank you so much for coming on and talking about humid buildings today.
Thank you, and thank everybody that showed up, and I appreciate the time.
All right. And my final sign off, as you can see, the AABC annual meeting is being held in Scottsdale, Arizona this year in October 11th through 13th. So now is a great time to head to aabc.com to reserve your room or to sign up as an exhibitor. And final thoughts, we are also interested in 1 to 2 more case studies to review for the final program. So if you're interested in sharing a case study this year, please visit aabc.com or learn more by emailing info@aabc.com. Thank you so much for joining another Tab Talk, and thank you to Ameritech for sponsoring, and have a wonderful evening. Bye all. See you next time.